Okay, so today we are talking about antiderivatives and integrals. And there's a slight difference between the two, but they are connected, and we'll learn that they're connected a bit later when we talk about the fundamental theorem of calculus. But so let's start with an introduction to these two ideas: an antiderivative, um, the integral. So the antiderivative is, if essentially it's the opposite of taking a derivative. So if you're asked for the antiderivative of some function f of x, that is the function capital F of x, such that the derivative of the antiderivative function is equal to the original function that you started with. Okay, so this is what defines being an antiderivative. On the other hand, the integral, which is usually going to be denoted as an S from, like this S symbol, this elongated S stands for integral, and it's an integral from a to b of some function f of x dx, is the area below the curve being f of x from a to b. So below the curve f of x from a to b. So these are the two notions that we're introducing you to today. And then the idea is that the two are connected to each other via the fundamental theorem of calculus. Okay. And what we see is that in number one, at least, we see that we're using this notation, which is an integral notation, to stand in for the antiderivative. So we really do just think of these two ideas as being the same thing, even though we haven't shown to you yet that they are actually the same thing. Okay, now let's go ahead and compute some of these integrals. Right, so you should remember that the derivative of the exponential function is just the exponential function. And so the first term is just going to be 2e to the x. Right? You take the derivative of this, you arrive back at the original guy. For this 9x squared, you have to think about the power rule in reverse. So the power rule, normally what you do is you pull the exponent down and then you subtract 1 from the exponent. We reverse these steps now. So instead, we add 1 to the exponent and then we divide by that new exponent. So that's going to end up being negative 3x cubed. And you can check that. If you take the derivative of this, you end up with the original negative 9x squared. For the last term, well, I'm going to introduce what's the general power rule for integrals, or the reverse power rule. So power rule for integrals, which says if you're integrating x to some power, where this n is just any number, then what you do is you increase the power by 1 and divide by that new power. And then you have to tack on a plus c at the end, because this integral is actually a general, the result is going to be a general function. You can shift the function up and down by some constant, which is what that plus c is doing. And the fact of the matter is, if you take the derivative of the right-hand side, that constant is going to disappear. And so you end up back where you started with the inner function. So that's why you have that plus c always. The one caveat to this is that n cannot equal -1, because if it were equal to -1, this right-hand side would not be defined. You'd be dividing by 0. And we'll get to that shortly. Okay, we'll get to that in part C. But this is already sufficient to answer part A. So what we do to this 3/5 is we add 1 to it. It's going to give us x to the 8/5, and then we divide to get 5/8. And we're adding, and then we do a plus c at the end. Okay. So that's that. For part B, you have to think through your derivatives of trig functions. What derivative will give you cosine? Sine derivatives give you cosine. So the first term is 3 sine of x. For the second term, what function will give you secant squared when you take its derivative? Well, that's going to be tangent. So you have 2 tangent x. And then lastly, what function is going to give you sine when you take its derivative? Well, that's going to be negative cosine. So you have a minus 5 cosine. And then plus c at the end. Okay. Next, we've got this secant tangent. So thinking through your trig derivatives, you'll remember that secant's derivative is secant tangent. So this should be secant theta. And now we hit this, I can pull out the 3, but then I'm going to have a 1 over theta, or 1 over x. And that is actually this case of where power rule breaks. So what you should remember is that there is a function whose derivative is 1 over x. And that function is the natural log, so ln of x. But we introduced something kind of special to this. We actually introduced absolute values around the x. And the reason for that is because it expands the domain in question. So it's sort of a technical reason, but we do need to put these absolute values when we integrate this 1 over x. So just remember to do that, you'll be fine. So yeah, the second half of part C is 3 ln of absolute value of theta, and then plus c. Okay. For D, well, I can pull the 4 out, and then I have a 1 over 1 plus x squared. This time, we have to think about the derivatives of inverse trig functions. And so if you think through those, you'll remember arctangent has this as its derivative. So we can write that down. And then the last two, I'm going to want to rewrite these as x to some power. So square root of x is x to the 1/2. That's x to the negative second. And so now I can just use the reverse power rule, or the power rule for integrals. So this x to the 1/2 is going to become x to the 3/2. And then we would divide by 3/2, but we may as well flip that over. So we multiply by 2/3. And this x to the negative second, when we add 1 to it, it's going to be x to the negative 1 divided by negative 1, which is the same as just multiplying by negative 1. And then we plus c. Okay. Are there any questions so far?
Yeah, I have one question. No matter what on these, basically you'll always add C.
Yes, yes. When it says general antiderivative, that generalness is because of the plus c.
Okay, that makes
Right,
sense. Thank you.
that's what it corresponds to. Yeah, because like it could be any constant. Like that constant could be 7, could be 12, could be pi, could be any number. The fact of the matter is, like, we don't have something that specifies what that constant is supposed to be. We're gonna get to that actually with number 2. So yeah, but in general, like, yeah, we can shift the entire function up and down. And the thing is that when we check that what we found is the antiderivative, what we do is we take the derivative of the antiderivative and we see, does that match the original function we started out with? And that whenever we take that derivative, that constant is always going to disappear. So yeah, these are the general antiderivatives. But with number 2, we see, where's my mouse? Okay, with number 2, we're actually given something extra. We're given a condition like this. This condition actually pinpoints for us which function. Like there's only going to be one function that passes through this corresponding point. And so this condition is going to specify for us what the value for C has to be in order to satisfy both things. All right, so let's go ahead and do that. So for number 2, what we're supposed to do is we're supposed to integrate this f prime function in order to figure out the just f of x, right? Integrate it or find the antiderivative. They mean the same thing. So when we integrate this, we get sine of x plus 2x plus c. Okay, now we use this condition. So if I plug in pi, I'm supposed to get 5. So f of pi, well, sine of pi is equal to 0. So we end up with 2 pi plus c is supposed to equal 5. And so solving for c, we get that c is equal to 5 minus 2 pi. Okay. So this finds for us what the value for c is supposed to be. And lastly, we should rewrite the function, but with the constant plugged in. That way we've specified the exact solution. Plus 5 minus 2 pi. So there we go. Okay. And now number 3 is doing the same thing, but doing it twice this time. So we have the second derivative, and we need to go back to the original. So that means we have to take 2 integrals in order to reverse the 2 derivatives. So the first integral is going to give w prime of x, the first derivative. So that's 5e to the x plus 2x plus c. And now if I use this first condition, w prime at 0 is equal to 3. That's going to give me 5 plus 0 plus c, so 5 plus c is equal to 3. So c is equal to -2. And then we can rewrite that just before we actually integrate it yet another time. Okay, and so now integrating it one more time, w of x is equal to 5e to the x plus x squared minus 2x plus, and now we should add another constant. So I'm gonna say d instead because we already introduced c in this problem. You could just use c again, but I'm gonna separate them out just because these two constants actually have different values. Okay. And then we use this condition that w of 0 is supposed to equal 9. So if I plug 0 in, we get 5 plus, both of these terms are 0. 5 plus d is supposed to be 9. And so then d is equal to 5 minus 9, which is 4. Okay. Lastly, I will rewrite the whole function with the constant of integration plugged in. And so there we go. Any questions? Oh, okay. Right. So number 4 is actually takes up the entire page. There are a bunch of different parts, but we start off with essentially the same thing we've been doing. It's just some more variables are introduced. So here we've got the second derivative function, which is actually just a constant function. I'm trying to draw straight, but I can't seem to. And we have these initial conditions, h at 0 and h prime at 0. But instead of giving us actual numbers, it just gives us 2 extra variables, h naught and v naught, but you can treat them as numbers, and you'll see that like it's the same thing as what was just done. So we integrate it one time to go from h double prime to h prime. And so, well, I guess in order to spell this out, maybe I'll say we're integrating this function negative 9.8 with respect to t. So since the function is defined in terms of t, we're integrating with respect to t. And we'll just end up with 9.8 t plus a constant. But the thing is, if we then also consider this condition, h prime at 0 is equal to v naught, what you'll see is that the constant is going to be that v naught. So I'm going to not write extra, steps. I'm just going to say like that this constant is supposed to be v naught. I hope that's clear. Let me know if it's not clear. For part B, it's the same thing. We integrate the function we just found to this negative 9.8t. We integrate that, that's going to divide it by 2. We get negative 4.9 t squared plus v naught t, and then plus another constant of integration. But this time we look at this initial condition and we see that the constant of integration is going to be h naught. So there we go. So these are our two formulas. And now C is basically specifying those two constants for us. We start off at a height of 2 meters. That's telling us that the h naught is 2 meters. And the initial velocity is 15 meters per second. That tells me that v naught is 15 meters per second. So yeah, that's just specifying those two constants for us. And so I can just rewrite the h function with these values. Okay. So that's that. And now D and E are just asking your typical questions about parabolas. So what time will the ball hit the ground? So the way that you would do that, the ball is going to hit the ground when the height is equal to 0. So you are going to solve for when h of t is equal to 0. And the thing is that this parabola, or this quadratic, is not very nice. You can't factor it or anything. You have to use quadratic formula, which you can write it out by hand. I'm not going to do that because it's just a bit of a hassle to write it out. But yeah, I'm just going to say quadratic formula here, and you should spell that out when you're showing all your work. There's like one step to maybe crunch some of the numbers to make it look nice-ish, and then I'll give you the decimal approximation. So 3.189 seconds. But yeah, there's no way around that. The numbers aren't nice. Okay, so that's D. For E, what time will the ball reach its maximum height? Well, so what you should think is that the ball is going to travel like this, and its maximum height is going to happen here, and at that maximum height, the derivative is equal to 0. So another way of saying that is that that's going to occur at a critical point. So really, we want to solve for when h prime of t is equal to 0. H prime of t is well, I'm going to take the function and just take its derivative. So negative 9.8 t plus 15. I set that equal to 0. I solve. That's going to give me that t is equal to 15 over 9.8. That looks like there's a decimal, but there isn't. 15 divided by 9.8. And unfortunately, that doesn't really simplify that fraction sort of stays that bad. Okay, so that answers the first half. Then what is the maximum height? So we found out when the maximum height occurs. All we have to do is now plug that into the function h. So plug that in. And well, again, this is the kind of thing you don't want to do this by hand because you have to square this decimal and all that. So I'll just write down what you get when you plug this into a calculator. 13.4796 approximately meters. Okay. Does that make sense? Any questions? Okay. So this is going to be the last page that we go over. And what's happening here is well, in the first 2 pages on this assignment, we've been dealing with the integral symbolically. We've been working with it as an antiderivative. Now we're going to work with it geometrically, and we're going to be thinking of this as the actual definition of the integral, which is the Riemann sum. So the area below a curve. Okay. And well, 5 is going to illustrate some of the basic properties that this integral has. So for 5a, what you see is we're looking at the, I'm going to just shade it in, but we're looking at this area, this triangle. And so going from -1 to 0, that's going to be 1/2 times base times height. So 1/2 times 1 times 2. So that's just 1. For B, we see it's going to be this other triangle. Base is 6 and height is 4. So it's this whole triangle. And the thing is that the area of the integral is actually, it calculates the signed area. So notice that this area, this region is actually below the x-axis. So we count this area negatively. 1/2 times base times height. The height is -4, so I can just write it like that. And then that's going to give me the value -12. And I can box these answers. Okay. Now, going from B to C, what happens is that we reverse the two limits of integration. So instead of integrating from 0 to 6 in part B, we're now integrating in the other order from 6 to 0. And that's kind of strange because we normally expect to go from left to right. But we can still think about this. What happens is that when we flip the order of the integral, we actually also flip the sign of the result. So one way I can do this is I can relate this back to problem B by saying this is equal to negative of the integral from 0 to 6 g of x, since it's written in terms of x dx. Okay, and so the answer for this part is 12. Okay, so if you flip the order of integration, you introduce a negative to the overall result. And lastly, for D, we have the integral from -1 to 6. So notice that like what we've done in the previous parts is we integrated from -1 to 0. We also integrated from 0 to 6. And now part D is asking us to integrate from the combined range, I guess, from -1 to 6. And so geometrically, what you'd expect to be able to do is to just add the two sub-problems, the two other integrals. And indeed, you can do that. So one way I can write this, I'm going to abbreviate. I'm going to just not put in g of x dx, but it's kind of clear like that's what I mean for both of these integrals. So what I can do is I can split that range of integration into two different pieces, and I can integrate over them separately and then tack the two results together, just add the two results together. So long as we cut on like the same value. So I'm cutting on 0. I'm just slicing in between. Okay, and so now this is just saying then I can add the result from part A to the result from part B. So yeah, 1 minus 12, which is negative 11. So that's the answer for D. Any questions? Make sense?
Yeah. So is that just like the area that that
Yeah.
confuses me a little bit?
Yes. So yeah, these integrals are representing area below a curve. So in particular, the difference is that these integrals have these limits of integration, right? They have these numbers. So what we call these things definite integrals. If it doesn't have these limits, those are called indefinite integrals. The crucial idea here is that when you have these limits of integration, the result is always going to be a number. And that number is going to correspond to an area, the area below the curve. Does that make sense?
Yeah. When you say below the curve, what do you mean? Like below y equals 0? Is that what you're talking about? Or below or above, I guess.
Below y equals 0. That's right. Yeah, so normally we want it to, well, not below y equals 0, like from the function to y equals 0.
Yeah.
So yeah, so in general, I guess that this is not what the general picture would look like. Maybe if I do it like that. Um, yeah. So when we say below the curve, it's usually because the curve is normally above the y equals 0 line, but we're always connecting it to the y equals 0. And so the part in red is counted negatively, but then the two parts that are in blue are counted positively. So the area in question is actually a signed area where we account for this positivity, negativity of the area, right? So in this case, it's not below the curve, but that's because the function is actually below the x-axis. Does that make sense?
Yeah, that makes sense. Thank you.
Hmm. Yeah. Okay. All right. So now for number 6. Yeah. So number 6 took me a while to explain in the previous class. So this is kind of how should I say this? Mm, well, so I get yeah. So the thing is that for number 5, the areas that we were calculating were really nice and easy to deal with because we were dealing with triangles. What happens in this problem is that we no longer have these kinds of nice shapes. So um, the idea is that to calculate the area, right? So if we were to calculate, this is asking us to estimate the integral from 0 to 6. The thing is that, so as you can see, like you would have to calculate the area of these two regions. If we were to do this completely precisely, we would have to calculate these two and calculate this area and subtract this area off. The problem is these areas aren't nice. They're not polygons that you can work with, that you can just create formulas for. That's why we need to do these kinds of estimations. And so we're going to learn about these kinds of left endpoint approximation and right endpoint approximation. Both of those come up in this course. And the idea is that we can subdivide the full interval from 0 to 6 into these subintervals. In particular, it's asking us to subdivide it into 3 different subintervals. And the the overall idea is if you let n go to infinity, if you subdivide the intervals smaller and smaller, then your approximation is going to approach the integral. It's going to approach the area below the curve. So maybe a picture might help for this. So if we simply were to draw something like this, so say that we're integrating from A to B, and we're trying to calculate this area below the curve. Well, the idea is we will end up subdividing this into however many regions. And um, for each subinterval, we would want to assign a rectangle with a particular height to it. And so if you let the number of subdivisions approach infinity, you can see that the widths of the rectangles get smaller and smaller, but then the kind of error that's introduced for each rectangle also gets smaller and smaller. So then in the limit, as n goes to infinity, the approximation with rectangles is going to approach the area below the curve. So that's why these approximations make sense, right? If you take the limit as n goes to infinity. Now, to explain what this left endpoint means. So I'm going to do that with the actual picture because it's larger and there's more detail. So first of all, I want to divide this interval from 0 to 6 into 3 subintervals. So that means that each width, the width of each rectangle is going to be 2. So we have a rectangle from 0 to 2, from 2 to 4, and from 4 to 6. And for each subinterval, I want to assign a height to that rectangle. Okay, so the left endpoint means that we make the height of the subinterval match the left endpoint of the subinterval. So for example, the subinterval from 0 to 2, well, its left endpoint is 2. So then we would make it match the height at 2, which is going to be, in this picture, -1. So for this, for this subinterval, we get this rectangle. If instead we were asked to find the right endpoint approximation, we would make the height of the rectangle assigned to this subinterval. We would make it match the height at 4. And there's another approximation method that you don't learn about in Calc 1, although you totally could, where it's called the midpoint approximation. You take the midpoint of your subinterval. So from 2 to 3, or sorry, 2 to 4, the midpoint would be 3. And then you could make the height of the rectangle be the value that you get at 3, which would be somewhere around there. So these are 3 different approximation methods. They're just ways of assigning a height to the particular rectangle in question. That's all that you need to take away from that. Okay, so now let's do it for the rest. So the subinterval 0 to 2, the height is going to correspond to the left endpoint, since we're using left endpoint approximation. So that's going to be 2 in this case. And then for the subinterval from 4 to 6, we match the height at 4, and that's going to be -4. So we end up with a rectangle height -4. Okay, so these are the rectangles that are approximating the area. And as you can see, like, this is really not a good estimation, but that's just because n is equal to 3, not 3 million. Okay. The last thing is we want to actually calculate this, the actual area that's estimated using this approximation. So, well, notice that the rectangles all have the same width. So what we can do is we can factor out that width and then just add the heights. So they all have the width of 2. And then I can just add together the first rectangle's height, the second rectangle's height, that's a -1, and then the third one is a -4. Okay. And I didn't need those extra parentheses. I'm just sort of saying it is you're adding all the heights together. This is -5 plus 2, -3. So we end up with -6 as our approximation. Okay. So any questions? Well, if there aren't any questions, then we can end here and we'll go through the rest next time.
Thank you.